Hi everybody, I'm glad to be here. So today I'm going to demo how to do machine learning with the Wolfram language, and also the outcome of this, that is to say the function, the high-level function that we make and that are based on machine learning statistics and that we train with our own tools. Okay, so first I start with a quick introduction about what is the Wolfram language. So this is the programming language of Mathematica, which is known, for example, for symbolic computation, like you can find closed-form solutions to symbolic equations. So it is now 30 years old. It has more than 5,000 of functions. So you can see it as a set of functionalities. And we offer, so in various domains, these functions. And they are high level and coherent, with which they are designed so that they will chain together well. And so, yeah, the purpose is that the users can make a powerful program in a few lines of codes. And the user doesn't really need a strong coding skills to do something. So maybe I demonstrate it here. So I wrote a little program here with 2 lines of code, which is going to blur the image, the faces in an image. So if I define it, and if I run it on an image, so yeah, it's blurring the faces. So it's possible to write it into lines of code because there are functions like find faces, to find faces, to blur an image. There are high-level functions. So what is great also is that the notebook, it's the main interface with the language, and it gives you regular feedback about what you are doing. It's also possible to write script in text and to run them, of course. There is also a polished, a good documentation. For example, if I click on this function, I have a documentation page, and it's also a notebook, actually, this documentation page. So I can run the examples here, and if I want to see the effect of one variable, for example, I can rerun it as I want. Okay, a good thing also is that in Mathematica, in the notebook, you will have access to the Wolfram Alpha database. So Wolfram Alpha, for those who don't know, is a service of question answering on factual answer. And inside the notebook, I can do a request like this in a language natural processing. For example, what are the notable people from Kiev? So it needs an internet connection to communicate with the Wolfram Alpha server and the knowledge base, and then it's answering with a list of people and their birth date, and they are all from Kiev. And this that we see here is a Mathematica expression. So it's this one here. So you can write it in plain text if you want, and if I evaluate it, I will have the same results. And there is also the possibility to interpret, to transform a plain text into one of these entities. Okay, so now I'm going to present the machine learning. So there are three steps, we can say. There are tools to train, evaluate, and deploy the models. There are also pre-trained models that are available. And then there are high-level applications which we are making in my team, which are based on the model that we train and that are doing things. So, for example, to train, it's we have classification and regression, and also in unsupervised learning, we can do clustering, dimensionality reduction, and also a hot topic now is probability density estimations with functions like learn distribution or some applications that are direct from this, which are anomaly detection, detect the examples with a low probability. Okay, there is also a model zoo. So, in particular, I will present, there is a big repository of neural networks that are pre-trained. And as I said, so from these tools, we are building high-level applications to process images, text, and audio. So I'm going to start with, to demo this, the kind of applications that we build that are based on machine learning models, and most of the time now it's deep learning. So for example, in object recognition, we have a function image identify. So you see in this image, it recognizes Easter egg. Another application is extracting high-level features. For example, from this image, we can extract some features from the faces of the people. Like it's detecting the faces and estimating the age of the people, their gender, and their emotion on the picture. So we can do art also. So here, for example, I have a picture of Kiev and a drawing of Malevich, and I want to redraw the picture of Kiev in the style of Malevich. So we have a function like this, imagery style, which is based on state-of-the-art neural networks also. I forgot to demo a cool thing also. On my previous example, so I can, this is taking a picture from my camera. I can make it dynamic, like in real time. And if I can apply in real time the blur faces function that I defined before. Sorry, I forgot to demo, but sorry, it's blurring my face. Okay, so you see you have this interactivity and these high-level functions to play. Some examples in natural language processing also. So there was a recent progress in reading comprehension in deep learning. So for example, we developed question answering. So here, for example, I took a Wikipedia page of Sergei Polonin, a ballet dancer from Ukraine. So you see, I can query from Wikipedia. So I have a big text like this. And here I'm going to ask on this big text a question: what is the nationality of Sergei Polonin? And then I ask to have the 3 answers and to display the highlighted sentence. And then it's answering highlighted what can be the nationality of Sergei Polonin. So this is based also on neural networks. Also on entity recognition, and more actually, it's about extracting in a text all the objects that have a semantic meaning. So for example, I give here a little piece of text about Ukraine and Kiev. And it's extracting so things like country, cities, but also colors and quantities. And what you see in the column interpretation, it's a Mathematica object also. Like it has interpreted the quantities, and you can, for example, after convert the quantities, you can do whatever you want with this kind of objects. And in this model, what is good is that it's doing disambiguation also, like the word dog. Oh, there is a display problem here. The word dog has different meanings, so the model is recognizing that the first occurrence corresponds to an animal, and the second occurrence here is corresponding to the food. So what we are seeing is a data set with every element has several attributes, like a type and the position in the text, the probability of recognition also. Okay, here, for example, I took the Wikipedia page of Kiev, and I'm asking what are the people that are mentioned in this page, and I'm asking also to output it as a list of entities which are in the database of Wolfram. Okay, and now I'm asking here to select all these people which are born in Kiev. So which have the property place of birth equal to Kiev. Okay, I have these ones. Here I'm displaying for all these people. I'm asking for what are their occupation, what are they known for. Okay, I have this. And now I take the same function that is going to grab information into text. And I'm asking to look for this person, especially, not person in general, but these entities, and to give a snippet of text around the occurrence of this person in the text. And then you see that I can guess also from this piece of text that the occupation of these people also. Okay, a last example, on the Wikipedia page of Sergei Polonin, the ballet dancer. For example, I wonder where did he have an influence or where did he live around the world. So I'm going to find in the page all the mention of locations. And I'm asking to display the result as the string in the text and the interpretation, which is here a geoposition. So the geoposition is also a Mathematica object. Here I just transform my data. Okay, I group by all the locations to which strings they correspond in the text and the number of occurrences. And then I can plot in a map. So they have the weights here. The size is proportional to the number of occurrences in the text. And then I can watch all the locations in a map. Okay. So now I'm approaching all the pre-trained classifier that we are offering in the language. So not all the classifiers that we train give birth to a function, because the number of functions would explode. So what we are proposing also is to have some pre-trained classifiers, and they are identified by a string. For example, there is a pre-trained classifier for notable person that I can run on images, and it's recording Mila Jovovich on this picture. Also for text, there is a spam detector where you can input a text. Then here it's understanding that the first is not a spam and the second is maybe a spam. There is, of course, sentiment analysis also, so you input a text and it's outputting a class. Okay, I can ask, by the way, some other properties. I can have the output probabilities. Of course, it's useful for many applications to have a confidence course on the answer. Okay, and for deep learning, we have we made a big effort to make a repository of network, which have now more than 70 models, and it's increasing. Like we are regularly importing all the pre-trained models that we find on the literature, and users can also participate, of course, to build our model. So there is this website where they are sorted either by input domain or by task type, and for each of the models, you will have a documentation page, so you can also download it from a notebook, like from Mathematica, and it's giving you some examples of how you can use the model. So it's a doc page which is showing what are the simplest code to run to have some interesting things with the model. So models are objects. For example, here it's a chain of layers. So it's a deep neural network. Each line corresponds to one level of the neural network. And I can apply it directly, this model, to an image. Like what cool thing is the pre-processing is included in the network, in the post-processing also. So here I give an image, and it outputs a geoposition, and then I can plot a local map around this position, for example. So here, I tried with a more complicated image of a beach. So I choose a beach in the east of Ukraine, and of course it's more complicated to identify beaches. So here, instead of plotting one result, I plot on a map for the 31st best hypothesis. Where are they? And the circle is proportional to the probability of the location. So it's not finding the right place here. It's finding some place where there are some harbor. Okay, there is also a network to colorize. So this one, the pre and post processing cannot be in the network. So we have to make a little functions to use it to do something. So this is also explained on the website for this model, what to run. Then if I give some black and white images, it's returning me the images in color. For text also, so for text, one of the most interesting things for transfer learning in text are word embeddings. So, for example, the glove models, word track, this kind of stuff. So to demo this, for example, I define two lists of words, one corresponding to animals and fruits. And here I am asking, given this model, so word embeddings just map each word into a vectorial space, which is supposed to be semantic. And here I'm asking feature space plot is doing a dimensionality reduction in 2D so that you can visualize your feature. And so you can see that words corresponding to animals will be together and words will be corresponding to fruits will be together also. And also recently I want to mention this model which is pretty cool from Allen Institute. It's called Elmo, and it's not doing simple, it's also word embeddings, but word embeddings in context, which means that the vectorial representation of a word depends on the words around it. So what is it doing? So it's a network like this, where it's first mapping each word to a vector, and then there is recurrent neural networks on these vectors to output some vectors that depends on all the context. And as they published the model, the Allen Institute, there are 3 outputs of this model that we see here, here, and here. So if I apply it to a string here, so with hello world, it will output 3 matrices. Here I plot them. So these are 1024 dimensional vectors, and there is one vector for all the words and all the tokens, words and punctuations, so hello world and exclamation mark. And the author, they recommend to average it. So to do it, for example, I can do some what we call surgery to the network, to manipulate it. And here I just take the 3 input here and add a new layer here, which is going to combine them and average them. It gives me another network. So that is a contextual word embeddings. And so here I am going to give some sentences with the word apple appearing in different contexts, like some of them mean the fruit, some of them mean the company. And if I do a feature space plot again of this word apple, in this different context, you see that it's grouping all the apples that means company together and all the apples that means the fruit together. Okay, so now through this slide, I'm going to demo how to train a machine learning. Here it's a classification task from the gathering the data to deployment. So here I define a function to scrape on the internet given a string that is a research. And I decided to build a problem with 3 classes, which are kind of soup. So I'm going to classify images of soup. So it's taking a bit of time now to download the images from the internet corresponding to these 3 classes. So I will make the union of them. Then I'm going to shuffle my data to split into training and the test set. And I'm going to run a classifier when the download will be finished. So I'm going to split into 80 samples to train and 40 samples to test. Okay, it's almost finished. Sorry about the time. It's downloading the 3rd class. So I'm going to train it, and you see here you got there are high-level options to the training, like you can specify a time goal, like I want to train it a maximum on 20 seconds here, because I'm presenting, so it has to be fast. You got also some option like performance goal, where you can choose between memory to optimize the memory of the model, or the speed, or the performances. Okay, so now my data is downloaded. So here are some 5 examples taken randomly from the training set. And now I'm learning them. So it's pre-processing the data. So yeah, what is it doing here? Processing the data, it's applying typically neural networks to find some high-level features, and then training some simple classifier on it, because of course there are a few training samples. So here, yeah, I got several panels here. It's not showing up correctly here. Okay, but at the end of the training, it gives me a classifier. Then I can apply this classifier on a test set, and it will output me an object, classifier measurement object. So let's see. So you see on the doc page that you can ask then a lot of properties. For example, you can ask for the confusion matrix on your test set. You can also, what I find cool also is you can ask for the worst classifier example, that is to say the examples that the model classify badly with a high confidence score. You can do this kind of stuff. After here, I'm defining a from function where you can apply your classifier from an image. I'm not in the right folder, sorry. Yeah, we didn't see the image, but let's deploy it. So here, I'm going to deploy it in the cloud, and it's going to generate a URL like this. So I can shorten it so that you can also try it. And you see on this page, I can load my image of a soup, and then it's going to classify it. So yeah, here the display is not very nice, but it's because I did shortcode, but of course you can polish and have some more funky stuff. Okay, so behind these tools, automated machine learning, I think, is a challenging task. It's about automatizing the work of a data scientist, let's say. But you're not going to lose your work, don't worry. So one of the challenges is feature extraction, like mapping any kind of object, images, text, audio, and in Wolfram Language we have other kind of objects like colors or 3D images. You have to map this into some numerical vector or sequences before doing something. So here this graph, it represents what is done internally, like there is a chain, automatically find chain to map any object to a numerical vector. And then it's trying several models on your task and trying to optimize on the validation set. So it has a pool of models, like it can be KNN and SVM for pattern matching methods. There are neural networks, logistic regression, random forest, gradient boosting tree, all the state-of-the-art classification model. Then what is it doing is that it's first training them on a few subset, on a small subset of your data, on small data, so that it's fast, to find all the best configuration. And at each round, it's eliminating the configuration that do not work and continuing to train on more data on the data. And then at the end, you will have a learning curve, which is to say the performance with respect to the number of training samples. So yeah, I should speed up actually, so let's not demo this. Okay, and there is the neural network framework. So yeah, so that's the kind of things we are proud in the company. So we don't have so many users, but we find that it's the most polished high-level framework without any performance sacrifices. So we made it very user-friendly. So first, it's interactive. As you saw, you can watch the graph of the models. When you train it, you have a panel that show up. We are going to see it. Also, there is an automatic support for variable length sequences. That's the things that the framework usually don't propose. For example, when it's training, it's gathering together all the sequences with a similar length in the mini batches, so that it will optimize the speed of the training. So all these kind of things is done automatically for you. as we saw, we have a repository of pre-trained network that is big and increasing. Also, it's easy to do neural network surgery, so to manipulate the network, to remove some layers, add some new layers uninitialized. These kind of operations are easy. Also, as I mentioned, the pre and post-processing are included in the network, so it's all together. Because if you have a neural network but you lose the pre-processing step, like you cannot do much because if you miss the first step, then the neural network is not going to work well. Also, there are automatic checks of constraints of the size of the layers, for example, and you've got human-readable errors when you've got an error. So, for example, if I take a long short-term memory, so an LSTM, so it's taking the number of features first, and then I can define the size of the input. But this kind of recurrent layer, it needs a sequence as input to make sense. So here, inputs goes to 3 means that I have numerical vector of size 3, and then it's complaining about this 3 and telling me no, it's expecting a matrix which is n times something. Okay, it's also performant. So we are based on the MXNet backend, and now we are supporting also multi-GPU and tensor core support with mixed precision, 60 and 32 bytes, in order to speed up the training. And of course, there is a nice documentation with some tutorial pages. Yeah, like this one, where you've got several examples sorted by applications or this kind of stuff. Okay, what is, you also have the Wolfram support, like if your model is not working for some reason, you will have you can contact the Wolfram support, or we've got also a community website where you can post your questions, and we are always responsive to help the user and solve the bugs that they may discover. So I think the support is important for the companies. And the cloud deploy that I show you, the cloud deployment is also here for neural networks. For now, the neural network has to be not so much big so that it won't blow up also in the net. Okay, so as I mentioned, you can visualize your network. So here, for example, this is the elmo shown as a graph of layer. So here it's the highway connections. So you can see the nonlinearity which are plotted here. And for example, if you wonder what is here, you can click here. See, okay, here it's a chain of layer with a convolutional layer and aggregation layer to do max pooling. And you can click, for example, again on the convolutions to see all the parameters of it. So to do debugging, it's pleasant. And what is cool also is that you see the size of the input and the output tensors. So it's easy to understand what's wrong. So if I put my mouse also in an edge here, I see the size of the tensor going in the network. Okay, so here, for example, the elmo, maybe I have a little time to explain, okay, what the elmo is doing. So first, this is a graphical representation of this network. So what the elmo is doing, first classical word embeddings, where it's just mapping with a lookup table each word to a vector space. No, sorry, it's mapping the characters, because actually what is cool with this model is that you don't have out-of-word vocabulary, which means it works on the characters. So as long as you work with a set of characters that is recognized, you don't have any problem of unknown words or this kind of stuff. So it's mapping all the characters to a vector, and then it's applying convolutions on the characters at the word level. Then there is a max pooling of this. So actually here we are the max pooling. After the max pooling we are here. So actually the convolutions have variable filters like 1, 2, 3 up to 7, and you combine all these convolutions together. Then there are some nonlinearities with highway networks, and then in the end you've got recurrences, which are this stuff here. So recurrent neural networks on top of this. So the max pooling is done on each word after the max pooling, you have a vector for each word, and then you apply a recurrent neural network on this. Okay, this was another example, for example, of the neural network that is behind find textual answers. So I was demoing question answering. So it's using this network also with this huge graph. So you have two inputs, the text and the questions, and the question. And in the end, what it is doing is that it's pointing the words where begin and start the answers in the text. So it can be represented like this. So one of the major components here is the attention layer. So the attention layer is a layer where you have a query and an input, and you're going to attend each element of the input. You are going to assign weights to all the elements of the input given the query and to combine this. So yeah, it's doing the two-way around. That is to say, it's looking at the text given the question and the question given the text and combining the two. So that's why in the end we have this complicated graph. Okay. So yeah, here I show an example how to train this neural network. So on the same classification task as before. So I take inception, a network trained on ImageNet. So yeah, a deep neural network again which is a chain of a lot of network. Then I cut his head, so I remove the first layer. I take only the 30 first layers. So you see the network originally it was given a tensor, a three-dimensional tensor, and outputting a vector of probabilities of size 1000. And now if I cut it, I stop a little bit before to have the probabilities. And then I will retrain a layer on top of this, which is like doing a logistic regression more or less on these high-level features. So in this command, I'm applying the network to my training data to have my features pre-processed. I could also train everything together, but so you see here I'm specifying that I want to use the GPU. Okay, now I construct another network which contains, which is going to be the head of the network, sorry. So it just drop out a linear layer and the softmax on top to have some probabilities. And then I can train this small network on my pre-processed data, which is the output of the data on the cutted inception network. So at any time also I can stop the training and it will give me the results. Okay, it's giving me my trained network. Now I join it with the feature extractor to have all together my deep network. And then I can apply it on an image to have the output probabilities. And again, yeah, watch the confusion matrix. All this kind of stuff. Okay, here I demo a little bit how to do some surgery. So yeah, here I took the network that is used for the function ImageIdentify that I showed in the beginning. And for example, I can define a function which given an image and a level of which level in the network I want to look at, which output me another image, a list of images actually, that correspond to the features learned on these images. Because in the neural network, so you see here the sizes of the tensor. So basically you begin with your image, which is a 3-channel, it's like 3 grayscale images. And then the number of features is increasing and the size of the image the number of features is increasing, sorry, and the size of the image is decreasing up to 1 by 1 to have only one vector. Okay, so I define my function, and for example, on the image of the Easter eggs, I can ask what are the features at level 5, and I can also have an animation, like here I'm printing, so I can do stop, otherwise it's maybe, okay. So yeah, this is an animation where, whoop, what did I do? Sorry. Well, let's rerun it. Sorry. Yeah, so I can watch interactively what are my features. And I can also, here I define a function to watch the learned weight of the neural network. And for example, here I'm watching the first convolutions, the weights of the first convolutions as images because they correspond to images. So here you are seeing as 3D images what are the weights. Okay, still neural networks stay a black box. As you see, it's hard to identify, okay, these features correspond to what. But still, we're proposing tools to try to understand what the neural networks is learning. Okay, so what's next? Yeah, so for machine learning, now our main activities for automated machine learning, there is a hot topic now, which is reverse generative models, which are neural networks, which are mapping data to a low dimension space to learn distribution on it, and they are reversible. So what is good is that you can sample from this model, because sometimes you can estimate the distribution, but you cannot sample from your distribution. But if your transformation is invertible, then you can learn the distribution and sample from it easily. So there are cool things happening in this domain. We are also very interested in few-shot learning. So when you have got extremely few examples, or things like meta-learning, learning to learn, this kind of things also is very interesting. For the neural networks, so we were a bit late for reinforcement learning. Like it was possible with our function net train to do reinforcement learning, but you needed to trick. So now we are working on offering a user-friendly interface to do reinforcement learning. We have an interface with OpenAI Gym, so we'll be able to do GANs, all this kind of stuff. We also want to offer the possibility to train directly in a GPU cloud. So on Amazon, on EC2 instances. So for now, we can specify CPU or GPU, and in the future, you can say EC2, and it will launch a machine on EC2 and run your training there. And also ONNX, which is a format for interoperability between frameworks, so that you can. So for now, we have tools to import from ONNX. And then in the future, you can also export on ONNX and use the model everywhere. So it's important for us that our user is not locked in. For example, for now, you can export the model in MXNet. And in the future, with ONNX, you can train the model in Mathematica and use it in PyTorch. All this kind of stuff will be possible. Okay, and some takeaway messages. So yeah, what I want to underline from a machine learning perspective is that transfer learning is important. Like when you have to, it's rare today that if you want to perform a task, you will design a network from scratch, uninitialize, then run it. It's better to find some pre-trained network to have some high-level features and to use them. Like it's very powerful. So you should never design a network from scratch. It's better to take the first layers, pre-train, and then to combine them. Also, I want to stress that the best solutions to be real-world application, in my opinion, most of the time they should not rely only on machine learning. Like machine learning is good if you've got a lot of data that explain your problem, but most of the time you have to put knowledge into them and to combine well the machine learning and knowledge-based approach. There's always a big knowledge base, or if you have prior on your tasks, then if you can inject it, you're going to find the best solution. So that's the difference between the pre-trained model and an application. Like maybe you need to combine your machine learning models with some other methods inside to have a meaningful application. And yes, the holy grail in this quest also is how to map all the modalities, so images, audio, and text, to a same semantic space. For now, people are doing it separately, but I think all the big companies, Facebook, they all want to achieve this, where you You put any media and it will project it into a semantic space that is common for all the modalities. Okay, so thank you. And you can also follow Steven Wolfram on Twitch, like now when we are doing design meeting, where we are designing the new functions. We are doing it live on Twitch, so you can also watch under the scene how we design our function, these kind of things. Thank you.
Round of applause for Jerome. Thanks a lot.